Let's take a look at the modern view of the atom. And we'll also take care of some of our notation and learn a little bit about how we'll use shorthand with these, and also bring up some of the units. Now notice that we're talking about something that's very small. 10 to the negative 10 meters is the size of a typical atom. Now let's make sure that we really appreciate how small that is. We'll have the number 1, and then we're going to have it 10 decimal places deep, so 2, 3, 4, 5, 6, 7, 8, 9, 10. Put a leading 0 so that we always identify the decimal point as being there. We're talking about this many meters. It's a very minuscule portion of a meter, and that makes a lot of sense to us. If I grab a meter stick, I'm not expecting to measure an atom using a meter stick. It's much, much smaller than that stick. So it's going to be very small, but notice how much smaller the nucleus is. In fact, we have to really pull it out in order to even see it, because it's 4 orders of magnitude smaller. Now, to give you a scale for that, that means that it's going to be that many decimal places further along. So it's going to be a really minuscule portion. All of that density for this atom is pretty much located in this little tiny spot. We have a small amount of mass in the electrons. They're minuscule for the mass. The nucleus is where most of that is, and that's why when Rutherford did his gold foil experiment, he actually saw that those particles were bouncing back off of the nucleus rather than going straight through like you would have expected with the plum pudding model. So a way of describing these charges is to assign them whole numbers. That way we don't have to talk about a really tiny number of coulombs, coulombs being the unit used for charge. And they did actually determine the exact charge back during the oil drop experiments, and you can find the values associated with that video. But when it comes to these charges, we're usually going to just speak about them in full-size charges. An electron is a -1 charge, a proton is a +1 charge, and a neutron will be 0. Now notice that we use a lowercase character for E, P, and N, and we put the charge in the superscript. With neutrons being a 0 charge, we make it a superscripted 0. That's how we'll describe their charges for these particles. Now the charge on an atom or a molecule is going to be written very similarly. We'll put it on the right side exponent. So if it's hydrogen with a plus charge, we'll put it right up there. A chloride ion with a -1 charge will be up here. A calcium ion with +2 will be up here. And an oxygen ion with a -2 charge will be up here. So we're always going to be putting our charges on the upper right-hand side. And you can see that we're consistent throughout all of this. But I really want to emphasize something here. We said that there's a lot of mass in the nucleus, and it's a really small volume. Notice that in this example, this is our fraction of the volume inside of the nucleus compared to the rest of the atom. Minuscule size, right? But notice how much of the mass is inside of it. 99.97% of the mass in a typical atom is going to be located in the nucleus, despite the fact that it's 10 to the -13th of the volume. Very, very dense. That's why instead of the 15-inch shell going straight through the tissue paper, as he used in his analogy for Rutherford's gold foil experiment, instead he saw that the particles were just ricocheting off, because all that mass is really localized in a very tiny space of the atom. That's also why most of the alpha particles went directly through that gold foil.